Dear students, today we'll see what do we mean by RC oscillator, and in that we'll see what is RC phase shift oscillator, and there also we will study a circuit of RC phase shift oscillator using an operational amplifier op-amp. Now here I am specifically saying op-amp because we can also build RC phase shift oscillator using BJT also. Okay. So here we will see today what is RC phase shift oscillator using op-amp. So here is the topic RC phase shift oscillator using op-amp, that is operational amplifier. So this RC phase shift oscillator is a circuit which will use resistors and capacitors. That is why it is called as RC. So RC is used, resistor and capacitor is used to introduce phase shift, whatever we require, so that the oscillator condition is met. This type of oscillator is used for generating very low frequencies. And here the 180-degree phase shift is obtained by the operational amplifier, and another 180-degree phase shift is obtained by the RC circuit, which we'll use in the feedback circuit. So that will be the background. So let's start with the concept of first, what is an oscillator? So as we all know, oscillator is a circuit which will produce repetitive waveform. So if you see a theory for oscillator, basic theory, what is an oscillator circuit? So an oscillator is a circuit that produces a periodic waveform on its output with only the DC supply voltage as required in. So here there is no specific input from outside. The DC supply voltage, whatever we are going to give, that will be working as the required input. An oscillator is an electronic circuit that produces a periodic signal. This periodic signal will be having a specific frequency and amplitude. If you see a waveform like this, so in this waveform, you can see it is repetitive waveform. Say this is one cycle, this is another cycle, this is third cycle. So this will go on. This is your time and this is amplitude. So here you can see the amplitude. This is the 0 point. This is the negative amplitude. So let this be minus A. This will be plus A. Okay, so here you can see the amplitude, and here you can see the negative amplitude. Okay, so this from the zero line, whatever we have is amplitude, and this from here till here, whatever time period is there for one complete cycle, that is positive and negative half cycles, that will be called as time period T, and a reciprocal of that, that is 1 by T, will be taken as frequency F. Okay, so here the periodic signal generated by an oscillator will be having a specific frequency. That means it will have one specific frequency. Okay, if you want to vary the frequency, there are many other methods, but when it is generating at one time, it will generate a specific frequency and amplitude. Then we also have studied conditions for oscillations, which were called as Bark-Hansen criteria. And in that, we saw that we are going to use an amplifier with a positive feedback. Okay, so here if you have a amplifier, this is an amplifier circuit. Okay, so this is amplifier circuit, and this will be your input and output. So this is input and this is output, and here you are going to have a feedback, okay, which is going to be positive feedback. Okay, so this is your feedback, and here you'll be having your feedback network. Okay, now here in place of this amplifier, in this amplifier stage, you can use active devices like BJT, you can use op-amp. Okay, that is operation amplifier, and these devices will be producing a phase shift of 180-degree. And then the feedback network, whatever you have, this feedback network should again produce a phase shift of 180-degree. So 180-degree by the amplifier and 180-degree by the feedback network. So it will be 360-degree phase shift in the total loop. And that 360-degree says that it is 0-degree. That means whatever feedback is coming is in phase with the input here. So it is in phase with the input here. And because of that, it is called as positive feedback. And that is one of the main important factor to have oscillations. And also the loop gain, that is the voltage gain of this amplifier and voltage gain of this feedback network. So like if the voltage gain of the amplifier is taken as A, and if the voltage gain of the feedback network is taken as beta, now this should be minimum equal to 1 or more than 1. Okay. So that is the loop gain should be unity or greater than unity. Clear? That is one more criteria of the Bar-Constant criteria for oscillations. And these 2 points oscillator circuit should follow so that the output can oscillate at a particular frequency. You can get a repetitive waveform at a particular frequency and amplitude. Okay. So here the conditions of oscillations are: the phase shift around the feedback loop must be effectively 0 degree. That is, we will make it 360 degree, and that 360 degree will be taken as 0 degree. And second point, the voltage gain around the feedback loop, that is loop gain, must be equal to or greater than 1. Okay. So that is the basic condition. Then we will come to the RC phase shift oscillator concept. And as I've told you earlier, here we are going to study RC phase shift using operation amplifier op-amp. Okay. So the op-amp based oscillator which produces a sinusoidal voltage at the output with the help of an inverting amplifier. So here we are going to use op-amp to build an inverting amplifier. Inverting amplifier will see that the input is amplified at the output, but it is in a phase reversal of 180 degree. And a feedback network is known as RC phase shift oscillator. So inverting amplifier and a feedback network together will be known as RC phase shift oscillator. This feedback network consists of 3 cascaded RC sections, that is, in series RC sections we are going to put. Now, what is this? What is this circuit? We will see. So here you can see the circuit of op-amp based RC phase shift oscillator. So here you can see the op-amp. So here you see op-amp. Now in op-amp, the negative terminal is given the feedback input. The input is given to the negative terminal, and the positive terminal is grounded. Positive terminal is grounded. So this op-amp is in inverting mode. So it is in inverting mode. Inverting amplifier. So it is in inverting mode. Now here RF and R1. This RF and R1 will decide the gain of this amplifier. So this is an amplifier whose gain will be minus RF upon R1. So that gain will be decided by this RF and R1 values of the resistors. Okay. And this is the output here. This is the output here. And from here, we are going to take a feedback. Okay. And in this feedback, you can see there are 3 sections of R and C, that is resistor and capacitor. So here you can see this is one section, this is one section, this is another section, and this is third section. Okay. Now here the two conditions of Bar-Constant criteria so that the circuit can oscillate. It will give you repetitive waveform. So in that the first condition was the closed loop phase shift should be 0 degree, that is 360 degree. And therefore we see here the op-amp, whatever we are using, the input is given here at the inverting terminal, and output you are going to get here. So if the input is say like this, output will be like this. So there will be a phase difference of 180 degree here. So there will be a phase difference of 180 degree. Now this 180 degree is there. So in the feedback network here where we are using R and C, we have to produce another 180 degrees so that the complete closed loop feedback and the op-amp phase shift will be 360 degree. So here we are having 3 RC network, and each of this RC network will produce 60-degree phase shift. 60-degree phase shift. So this 60 plus 60 plus 60, this will be 180. This will be 180 degree, and that 180 degree with the op-amp 180 degree will make it as 360 degree total phase shift of the loop. That is nothing but 0 degree. So this the first condition we have maintained. And the second condition, we will see that the gain of the amplifier here, which depends upon RF and R1 resistor, will be equal to, okay, equal to the reciprocal of the gain of this feedback network. Okay, so whatever the gain of the feedback network, that reciprocal should be the gain of the inverting amplifier. Say for example, if the feedback network is having a gain of 10, then the uh, this amplifier should be having a gain of 1 by 10. Okay, if the feedback network is having a gain of 1 by 10, then the amplifier should have a gain of 10. Okay, so that the overall gain is multiplied, that is amplifier gain and the feedback network. If you take the product, that product should be unity, that is one or more than one. So here, this is the circuit. Now here, we know that when we studied op-amp, whatever input we give at the inverting terminal will be 180-degree phase shifted at the output. It will be amplified, but it will be phase shifted. Okay. Now here, basically the feedback network, which is having three RC circuit. Now how these RC circuits are giving a phase shift, that we will see. So here you can see this is a RC circuit. So we have taken a C here, a capacitor, and we have taken R here. This is the input voltage V in, okay, and this is the output voltage across the resistor. We can call it as VR1, or this is the output voltage across the resistor. Okay. Now here in this circuit, the voltage of across the resistor, the voltage whatever you get across the resistor will lead by the input voltage, by 90-degree. If you take this resistor R1 as 0, if you take resistor R1 as 0, the voltage across R1, that is this voltage, will lead the input voltage by 90-degree. Now, if you take R1 as 0, then it will become a short line. There will be no resistance, there will be no voltage developed across it. And practically, this is not the concept where we can say when there is R1, that is the resistance is 0, the voltage can be developed across it. So here, to have a certain voltage, what we will do is we will see that the value of R1 is such that whatever voltage is developed across R1, okay, we will choose R1 such that whatever voltage is developed across R1, that is 60-degree in phase shift with the input voltage. So it is going to lead the input voltage by 60-degree. So in that way, we will choose R1, and that will make our RC phase shift network. So one RC combination is giving you 60-degree. Second RC combination will give you another 60-degree. And third RC combination will give you another 60-degree. So we'll have that 180-degree phase shift in the feedback network. So here is the theory for it. From basic theory, we know that if R is equal to 0, voltage across R will lead the input voltage by 90-degree. That we have seen. Adjusting R is equal to 0 would be impractical. So it is not practical because it results in 0 voltage across R. Therefore, R value is selected such that voltage across R leads the input voltage by 60-degree. If we cascade or put in series 3 RC network, we will get 180-degree phase shift. Okay, so that R1, whatever we have taken in the circuit, here we have mentioned as R. So R, if that resistance is equal to 0, then the voltage across the resistance will lead the input voltage by 90-degree. If you keep the resistance 0, it will not be a practical circuit because it will result in a 0 voltage across resistance. Therefore, the resistance value is selected such that across resistance, whatever voltage is there, that will lead the input by 60-degree. So that will see that RC network is giving a phase shift of 60-degree. So if one RC is giving a phase shift of 60-degree, we will have another RC, we will have another RC. So three RC network connected in series, which is called as a cascaded 3 RC network. Then we will get a phase shift of 180-degree in the feedback network. Now that phase shift in the feedback network of 180-degree and a phase shift in the op-amp, that is the amplifier network of another 180-degree, we'll see that both these 180 degrees are added, and the closed loop phase shift, the total phase shift of the closed loop will be 360-degree, that is 0-degree, which will give you a positive feedback. Okay, so a positive feedback in case of an amplifier will give rise to oscillations. Then it can be an oscillator circuit. So in the above circuit, what we saw using op-amp, the op-amp is in operating in inverting mode. Hence, it provides a phase shift of 180-degree. The feedback network present in the circuit also provides a phase shift of 180-degree. Since each RC section provides a phase shift of 60 degree, therefore the above circuit provides a total phase shift of 360 degree at some frequency. Okay, and also we'll see that the gain of the amplifier and the gain of the feedback network will be reciprocal to each other, so that the product will be unity or little more than unity. So the output frequency of RC phase shift oscillator is given as 1 by 2 pi RC root 6. So the output frequency of oscillations is given as 1 by 2 pi. R and C are the values of RC in the RC network multiplied by root 6. So if you take this formula, you will get the frequency of oscillations for an RC phase shift circuit. Then if you speak about the gain of an inverting amplifier should be greater than or equal to minus 29. So this is seen by the analysis, and after the analysis we have seen that the gain of the amplifier circuit should be equal to or greater than minus 29. So we should consider the value of feedback resistors RF as minimum of 29 times the resistor R1, because here the gain of the amplifier is given as minus RF by R1. So here you can see, if you draw this block diagram, this is an amplifier, this is an amplifier, and here you have a feedback network. Okay, feedback network, and this is the output, and this is the feedback, and this feedback we are going to give back to the amplifier. Now here, the gain of the amplifier, that is A or AB, anything you can denote it as, it is given as minus RF upon R1. And the analysis say for RC phase shift, this gain should be equal to minus 29, minus 29. So if you want to make this gain as minus 29, then the feedback resistor RF should be 29 times of the resistor R1. Okay, this is the one condition where we see that the value of feedback resistor RF is as minimum of 29 times the value of resistor R1 in order to produce sustained oscillations at the output of an RC phase shift oscillator. Now this is, here we say that gain of the amplifier is minus 29 and the gain of the feedback network will be 1 upon 29. Okay, so 1 upon 29 multiplied by 29 will be unity. So minimum condition for oscillation will be maintained. Then what are the advantages of RC phase shift oscillator? It is useful for frequencies in the audio range. It is simple in the circuit, there is simplicity of the circuit. They have a wide range of frequency. The RC phase shift oscillator gives good frequency stability. The output of the circuit is sinusoidal, that is quite distortion free. Then if you see the disadvantages, so here we have mentioned some disadvantages. RC phase shift oscillators are hard for the circuit to start oscillations. So the RC phase oscillators are hard for the circuit to start oscillations. The output is small because of the smaller feedback. The RC phase shift oscillator requires high VCC for large feedback. There is poor frequency stability. Then if you see some applications of RC phase shift oscillator, so you can see RC oscillators can be used to generate signals having a huge range of frequencies. They are used extensively in voice synthesis and musical instruments. RC oscillators are also used in GPS units. Okay, thank you, students.